Hello and welcome to Science Night Tales. I am glad you found this quiet moment to pause. Tonight we are going to step outside of time. We spend our days ruled by seconds, hours and schedules, units that feel incredibly real to us, but mean nothing to the universe. We are going to explore the concept of deep time. We will look past the noisy, bright era we live in now and look toward the long, silent future of the cosmos. We will see how stars turn into crystals, how planets drift in the dark, and why the ultimate fate of the universe is not destruction, but a perfect, eternal rest. There is no urgency here. The universe is not in a rush, and neither are we. You can simply let the scale of these numbers wash over you, shrinking your worries down until they disappear into the background. If finding peace in the vastness of physics helps you settle down, you are welcome to like or subscribe. For now, let go of the clock and let's drift into the deep future together. The human brain processes time in seconds, hours, and years. It learns to divide existence into manageable units: the duration of a heartbeat, the length of a breath, the cycle of light and darkness we call a day. These measurements feel universal because they are intimate. They are tied to the rhythms of biology and the slow turning of a planet beneath our feet. But these units are not fundamental. They are local artifacts. A second exists because neurons fire at a certain speed. A year exists because Earth follows a particular orbit around a particular star. Even history itself is measured by fragile markers: generations, lifespans, civilizations, each one bounded by the limitations of human memory. None of these scales are written into the structure of the universe. Beyond the thin shell of our daily experience, time behaves differently. On cosmic scales, seconds dissolve into irrelevance, years collapse into statistical noise, processes unfold so slowly that they cannot be experienced, only inferred. Mountains of time pass without events, entire galaxies change their structure, while nothing, from a human perspective, appears to happen at all. Modern cosmology has begun to reveal just how misplaced our intuition about time truly is. Measurements of the cosmic microwave background, the faint afterglow of the early universe, suggest that our calculations of cosmic expansion do not fully agree with observations of the present universe. This disagreement is known as the Hubble tension. At first glance, it appears to be a technical problem. Two methods of measuring the same quantity yield different answers. But beneath the mathematics lies a deeper implication. If the expansion rate of the universe cannot be reconciled across epochs, then time itself may not function as a single coherent narrative. The universe may not simply be older or younger than we think. Our timeline may not apply to it in the way we assume. Human time is sequential. It moves forward moment by moment, carrying memory and expectation. Cosmic time is statistical. It is not experienced. It is averaged. It is inferred from states rather than events. The universe does not remember its past. It does not anticipate its future. It transitions between physical conditions according to probability and energy distribution. From this perspective, our era occupies an unusual position. We exist in a brief interval of high energy. Stars burn intensely. Galaxies glow. Heavy elements circulate through space, enabling chemistry, planets, and life. This period feels dominant because it is the only one we can observe from the inside, but it is not representative. Most of cosmic history lies elsewhere. Before stars ignited, the universe was dark. After stars exhaust their fuel, it will be dark again. The luminous age, the age of structure, heat, and activity, is a thin layer stretched across an otherwise silent timeline. What we interpret as the universe is largely a temporary disturbance. When stars burn, they generate noise, radiation, fusion, motion, complexity. But noise fades, energy spreads, gradients flatten. Given enough time, every system relaxes toward equilibrium. This is not philosophy, it is thermodynamics. The true baseline of the universe is not brightness, but absence. Not motion, but stillness. Not creation, but persistence. Silence is not what comes before activity. Silence is what remains after it. In this video, we will explore the concept of cosmic deep time. We won't examine space as a destination or a frontier. We won't frame the universe as a stage for exploration, conquest, or endless novelty. Instead, we will treat it as what it fundamentally is, a physical system governed by energy flow, entropy, and statistical inevitability. The universe is not evolving toward complexity forever. Complexity is a transient condition that emerges when energy differences are high. As those differences diminish, complexity dissolves. To understand this process, we will follow the universe not at its most dramatic moments, but at its most representative ones. We will examine rogue planets, worlds ejected from their stars, drifting through interstellar darkness. These objects are not rare anomalies. They may outnumber stars themselves. Their existence suggests that isolation, not illumination, is the default state of planetary matter. We will explore the physics of vacuum decay and metastability. Even the fabric of space may not be permanent. What appears stable on human timescales may only be conditionally stable across cosmic ones. Yet even these transitions, should they occur, do not favor chaos indefinitely. They resolve into new, lower energy configurations. We will consider the inevitable cessation of star formation. As galaxies exhaust their gas, new stars fail to ignite. The universe does not collapse into disorder. It slowly runs out of fuel for activity. Light production declines, motion simplifies, structures persist, but they no longer change in meaningful ways. Across these phenomena, a single pattern emerges. Chaos is temporary. What we call chaos, storms, explosions, stellar death, galactic collisions, is simply energy redistributing itself. It is motion seeking rest. It is imbalance correcting toward equilibrium. The long-term fate of the universe is not fire, but cold, not collapse, but diffusion, not violence, but quiet. This is not a narrative of destruction. Nothing is being taken away. Matter remains, space remains. Time, in whatever form it takes, continues. What disappears is urgency. In deep cosmic time, there is no event horizon for attention, no moment that demands focus, no climax toward which history strains. The universe does not build toward an ending. It relaxes into a state where endings no longer matter. This is the physics of rest. A universe where energy gradients have flattened, where motion persists only as residual drift, where structure exists without purpose or transformation, where change is so slow that it becomes indistinguishable from stillness. From within the human moment, this future feels abstract, distant, even unsettling. But from the perspective of the cosmos, it is ordinary. It is the condition that occupies the overwhelming majority of time. To understand the universe, then, is not to imagine endless expansion or perpetual drama. It is to recognize that stillness is not the opposite of existence. It is its most stable form. We live in a noisy time, not noisy in the sense of sound, but in the language of physics. The present universe is saturated with activity, light streaming through space, particles colliding, stars converting mass into energy without pause. From within this moment, such activity feels natural, even inevitable. The universe appears alive with motion. On cosmic timescales, this impression is misleading. The brightness that surrounds us belongs to a specific and temporary phase in the universe's history. Cosmology refers to this phase as the Stelliferous Era, the only interval during which stars exist as long-lived engines of nuclear fusion. This matters because stars are not merely objects in space. They are the primary source of organized energy in the universe. Every visible structure we associate with cosmic richness, galaxies, nebulae, planetary systems, atmospheres, biology, depends on sustained stellar output. Without fusion-powered stars, the universe is largely dark. The Stelliferous Era begins several hundred million years after the Big Bang, when the expanding universe cools enough for matter to clump under gravity. Vast clouds of hydrogen collapse inward. At their centers, pressure and temperature rise until nuclear fusion becomes possible. It will end when those conditions can no longer be met. As time progresses, the universe expands. Matter becomes more diffuse. Usable hydrogen is steadily consumed or locked away inside stellar remnants, such as white dwarfs, neutron stars, and black holes. New stars form more slowly, then stop forming altogether. When the last generation of stars exhausts its fuel, the Stelliferous Era quietly fades. On human scales, this era feels immense. It stretches across trillions of years. Civilizations rise and vanish in less than a heartbeat by comparison. But when the history of the universe is viewed on a logarithmic time axis, where early, rapid changes and extremely long futures are weighted appropriately, the age of starlight occupies only a narrow band. It appears as a brief luminous disturbance between much longer epochs of darkness. The brightness of this era is produced by a single, well-understood physical mechanism. Inside stars like the Sun, energy is generated primarily through the proton-proton chain reaction. At the core, gravity compresses hydrogen to extraordinary densities. Temperatures reach millions of degrees. Under these conditions, protons, normally repelled by their shared positive charge, are occasionally forced close enough together for the strong nuclear force to bind them. In the first step of the reaction, two protons collide. One of them transforms into a neutron through the weak nuclear interaction. This conversion releases a positron, a neutrino, and energy. The event is extremely rare for any individual proton, which is why stars burn slowly rather than catastrophically. Over vast timescales, these rare events accumulate. Protons and neutrons combine to form helium nuclei. In the process, a small fraction of mass is lost and converted directly into energy in accordance with the relationship between mass and energy. That energy does not escape the star immediately. Photons produced in the core begin a long, inefficient journey outward. They scatter repeatedly through dense plasma, colliding with charged particles again and again. This random walk can take thousands to millions of years. Only after reaching the star's surface does the energy finally leave as light, spreading into space. What we observe as starlight is not a sudden release, it is delayed energy, leaking outward because the fusion process is inefficient. This inefficiency is crucial. If fusion were highly efficient, stars would release their energy quickly and violently. Instead, inefficiency stretches energy release across immense durations. Stars glow steadily, planetary orbits remain stable, chemical reactions proceed slowly. Complexity has time to emerge. From the perspective of life, this makes light appear abundant and dependable. But abundance should not be confused with normality. Light is not the universe at equilibrium. It is evidence that equilibrium has not yet been reached. It signals the presence of energy gradients, differences in temperature and density that still drive motion and change. For a biological observer, light seems fundamental because life can only arise during this luminous interval. This creates a powerful selection effect. We observe the universe from the inside of its brightest phase and mistake that phase for the rule rather than the exception. In deep cosmic time, the situation reverses. The universe spends the majority of its existence without stars. Before the first fusion reactions ignited, space was dark. Long after the last stars fade, it will be dark again. The Stelliferous Era is not the universe's default state. It is a temporary condition that exists only while fusion remains possible. Measured against the full lifespan of the cosmos, the era of light is brief. In logarithmic time, it is less than a blink. We are not observing the universe as it usually is. We are observing a temporary anomaly of brightness, a noisy interval in which energy is still being unevenly redistributed. When this era ends, nothing dramatic needs to occur. The universe does not collapse. It does not tear itself apart. Fusion simply becomes impossible. Energy gradients flatten, light production ceases, the noise subsides. What remains is a universe closer to equilibrium, colder, darker, and far more representative of cosmic time as a whole. The word void suggests absence. In everyday language, it implies nothingness, a complete lack of substance, structure, or activity. When applied to the universe, it evokes the image of galaxies suspended in an empty backdrop, separated by vast regions where nothing exists. This image is comforting in its simplicity. It is also incorrect. In modern physics, there is no such thing as truly empty space. What we call the void is not a philosophical vacuum, but a physical system with structure, properties, and measurable effects. According to quantum field theory, every region of space is permeated by fields. These fields are not objects placed inside space. They are what space is made of. Particles, electrons, quarks, photons are not independent entities drifting through emptiness. They are localized excitations of underlying fields that extend everywhere. Even when no particles are present, the fields remain. This means that so-called empty space still contains energy. At the smallest scales, quantum fields cannot be perfectly still. The uncertainty principle forbids absolute rest. As a result, fields fluctuate continuously. Energy briefly concentrates and disperses. Particle-antiparticle pairs momentarily appear and vanish. This restless activity is often described as quantum foam. The term is metaphorical, but the effect is real. On unimaginably small scales, space is not smooth. It seethes with transient structure, tiny ripples of energy that never fully disappear, even in the absence of matter. Nothing is happening, yet something is always occurring. This does not make space chaotic. The fluctuations are constrained. They obey precise statistical rules. Over large distances and long durations, their effects average out. The foam does not erupt into sustained motion or complexity. It hums quietly beneath everything that exists. From a human perspective, this activity is invisible. Between galaxies, the distances are so vast and matter so sparse that space appears empty. Light may travel millions of years without encountering an atom. But emptiness here is a matter of scale, not substance. The space between galaxies is not nothingness. It is a continuous physical medium. This becomes especially clear when we consider cosmic expansion. Galaxies are not flying apart through pre-existing emptiness. The distance between them increases because space itself is stretching. This expansion is not driven by matter or radiation, but by a property of space often described as dark energy. Dark energy is not a force in the traditional sense. It does not pull or push objects through space. Instead, it alters the geometry of space itself, causing it to expand uniformly. The farther apart two regions are, the more space there is between them to stretch. As the universe ages, this stretching accelerates. The result is not violent motion, but increasing isolation. Galaxies drift beyond one another's reach, not because they move faster, but because the medium separating them grows. This is the modern definition of the void. It is not an empty stage where events occasionally occur. Space is not passive. It participates. It evolves. It carries energy even when it appears empty. The vast regions between galaxies are filled with quantum fields in their lowest energy states and with dark energy that steadily enlarges the distances between structures. Matter becomes increasingly diluted. Interactions become rare. Over deep time, the void dominates, not because it consumes matter, but because it outlasts it. Stars burn out. Galaxies fade from one another's horizons. What remains is an expanding, low-energy field, quiet, uniform, and persistent. In this sense, the void is not the absence of the universe. It is the universe approaching equilibrium. Space is not a backdrop. It is a dynamic participant. And as time extends toward its longest scales, it is the void, not light, not matter, not motion, that defines the most common state of reality. There is a fundamental difference between how the universe exists and how it is perceived. What we experience is not reality in real time, but reality filtered through delay. Every observation is separated from its source by distance, and distance in the universe is inseparable from time. This separation is not a limitation of technology. It is a property of physics. Information cannot travel instantaneously. The maximum speed at which any signal, influence, your causal connection can propagate is the speed of light denoted as Yaozi. This limit is not a practical inconvenience. It is built into the structure of space-time itself. As a result, seeing is always an act of looking into the past. Light requires time to travel. Even on human scales, this delay exists. Sunlight reaches Earth after about 8 minutes. The light from nearby stars arrives years after it was emitted. Light from distant galaxies may travel for millions or billions of years before it reaches us. The universe does not present itself all at once. It reveals itself as a layered archive. When we observe the cosmic web, the vast filaments of galaxies stretching across space, we are not witnessing a synchronized moment in cosmic history. Each point in that structure is seen at a different time. Nearby galaxies are observed as they were recently. Distant ones appear frozen in far earlier stages of evolution. What looks like a single image is actually a collage of eras. In this sense, the observable universe is not a map of the present. It is a fossil record. The farther we look, the further back in time we observe. At extreme distances, we see galaxies in their infancy. Beyond them, we see only diffuse gas. Beyond that, we encounter the cosmic microwave background, a snapshot of the universe when it was still hot, dense, and opaque. There is no observational access beyond this boundary, not because nothing exists there, but because no information from earlier times can reach us. This creates a subtle but profound form of isolation. We never see the universe as it is. We see it as it was. The present state of distant regions is inaccessible to us. Whatever transformations are occurring there now, stars forming or dying, galaxies colliding or drifting apart, are hidden behind the finite speed of light. Their current condition exists, but it cannot be known. The universe we observe is therefore incomplete, not spatially, but temporally. Each observer occupies a unique position in space-time, defined not only by location, but by now. That temporal coordinate cannot be shared instantaneously with distant regions. There is no universal present that spans the cosmos. This is not merely a matter of perception, it is a consequence of relativity. According to modern physics, time does not flow identically everywhere. Motion and gravity both affect its passage. Clocks in strong gravitational fields tick more slowly than those far from mass. Objects moving at high speeds experience time at a different rate than those at rest. There is no single cosmic clock. Instead, there are countless local timelines, each valid within its own frame of reference. When combined with the finite speed of light, this means the universe cannot be observed as a unified, simultaneous whole. Even in principle, no observer can access the full present state of the cosmos. This leads to a quiet conclusion. We are surrounded by images of the past. The stars above us are memories. Galaxies are historical records. The largest structures in existence reach us only as delayed impressions, preserved in light that left them long ago. We exist at the center of our observable universe, not because we are special, but because observation always places the observer at the center of their own past light cone. Beyond that cone lies the unknowable present. Other regions of the universe are experiencing their own now, events unfolding that are real, but forever separated from us by time. Expansion increases this separation. As space stretches, more regions cross beyond our causal horizon, becoming permanently inaccessible. This is chronological isolation. We are not only distant from most of the universe in space, we are distant from it in time. No signal can tell us what is happening now in the far reaches of the cosmos. No future observation will close that gap. The delay is not shrinking, it is growing. From our perspective, the universe becomes increasingly archival. More of what exists slips into a category that can never be directly known. Not because it vanishes, but because it recedes beyond the limits of causality. In this sense, every observer is effectively alone in their temporal coordinate. We occupy a thin slice of space-time, surrounded on all sides by echoes. What we call reality is a carefully structured illusion, accurate, reliable, and consistent, yet always late. The universe does not wait to be seen. It continues independently while we observe only its after-images. Isolation is not an edge case in the universe. It is a dominant outcome. Within the Milky Way alone, astronomers estimate that there are billions of planetary mass objects that do not orbit any star. These bodies are not rare failures or exotic remnants. They are the natural byproduct of how planetary systems form. They are known as rogue planets. Their existence follows directly from the physics of gravity. Planetary systems do not emerge in calm, orderly configurations. They form inside collapsing disks of gas and dust, where multiple bodies grow at the same time and compete for mass and stable orbits. During this phase, gravity does not settle into balance, it oscillates. This instability is formalized in what physics calls the three-body problem. When three or more massive objects interact gravitationally, their future trajectories cannot be solved exactly. Small differences in position or velocity grow exponentially. Orbits exchange energy, paths cross. Long-term stability is not guaranteed. In young planetary systems, this chaos is amplified. Gas giants migrate inward and outward through their disks. Resonances form and break. When large planets pass near smaller ones, gravitational slingshots occur. Energy is transferred. One body is pushed into a tighter orbit. Another is accelerated outward. Often, the result is ejection. A planet can receive enough kinetic energy to exceed the escape velocity of its system. Once that threshold is crossed, gravity no longer binds it to its star. Its trajectory becomes hyperbolic. There is no return path. This process does not require violence in the cinematic sense. It is not an explosion. It is a gradual accumulation of orbital perturbations that eventually resolves into expulsion. The system stabilizes. The planet is lost. Once ejected, a rogue planet enters the interstellar medium. This environment is not empty, but it is extremely sparse. Particle densities fall to less than 1 atom per cubic centimeter. Temperatures approach a few degrees above absolute zero. There is no stellar radiation, no solar wind, no magnetospheric shielding. There is no day. There is no night. There is only the ambient microwave glow of the galaxy, the residual background radiation left over from earlier cosmic epochs. At the surface, conditions are static. Any atmosphere the planet once possessed quickly cools. Without stellar heating, gases condense. Nitrogen freezes first, followed by oxygen, carbon dioxide, and noble gases. Over time, the atmosphere collapses entirely, forming layers of solid ice that settle onto the crust. Weather ends, circulation ceases. What remains is a sealed world, entombed beneath frozen volatiles. From the outside, such a planet appears inert. Internally, it is not. Planetary heat does not originate solely from stars. During formation, heavy elements become concentrated in planetary cores. Among these are radioactive isotopes such as uranium-238 and thorium-232. These isotopes decay. Their half-lives span billions of years. Each decay event releases energy. Individually insignificant, collectively persistent. Over geological timescales, this radiogenic heating is sufficient to maintain internal temperatures far above the surface. In sufficiently massive rogue planets, this heat prevents complete solidification. Beneath the frozen crust, mantles may remain partially liquid. In some cases, subsurface oceans can exist, isolated, dark, and long-lived. This internal activity does not imply habitability. There is no photosynthesis, no surface chemistry driven by light, no exchange with the external universe. Any internal dynamics unfold slowly, sealed away from space. These planets are not alive in a biological sense, but they are not dead either. They exist in a thermodynamic middle state, cooling gradually, radiating heat into an environment that cannot return it. Their trajectories carry them through the galaxy on long solitary paths. They do not orbit the galactic center in neat loops. They drift, influenced weakly by distant masses, occasionally passing through spiral arms or molecular clouds without interaction. Encounters are rare, collisions are rarer. For most of their existence, rogue planets move through darkness without reference points. No sunrise marks time, no seasons impose rhythm. There is only motion through an almost featureless field. From a cosmic perspective, this condition is not exceptional. Bound planets, worlds warmed by stars, regulated by orbital cycles, are the minority case. They require stable architectures and long-term gravitational order. Rogue planets require only instability, which is common. Isolation, then, is not a failure mode of planetary formation. It is one of its most frequent results. These objects demonstrate a broader principle. The universe does not organize matter for visibility or accessibility. It does not prioritize illumination. Most planetary mass exists far from stars, disconnected from energy sources. We evolving slowly toward thermal equilibrium. Rogue planets are not anomalies, drifting at the margins of cosmic history. They are representatives. They show what planetary matter does when it is released from structured systems and allowed to follow the most probable path. That path leads away from light, away from interaction, toward isolation. Not all stars end in violence. The most common fate for stars in the universe is not explosion, but compression and cooling. Stars with masses comparable to the Sun spend billions of years on the main sequence, converting hydrogen into helium through nuclear fusion. This phase is stable precisely because fusion counteracts gravity. Outward radiation pressure balances inward collapse. Eventually, that balance fails. When the hydrogen in the core is exhausted, fusion can no longer be sustained at the center. The star responds by contracting. Temperatures rise briefly, helium fusion ignites. The outer layers expand, and the star enters its red giant phase. This stage is temporary. A star of modest mass lacks the gravitational strength required to fuse heavier elements beyond carbon and oxygen. When helium fuel is depleted, nuclear reactions cease permanently. The outer layers are no longer gravitationally bound. They drift away into space, forming a planetary nebula, an expanding shell of ionized gas. What remains is the core. This remnant is a white dwarf. A white dwarf contains roughly the mass of the Sun, compressed into a volume comparable to that of Earth. Densities reach millions of times that of ordinary matter. Under such conditions, atoms cannot exist in their familiar form. Gravity continues to pull inward. What prevents further collapse is not fusion, but a quantum mechanical effect known as electron degeneracy pressure. Electrons are fermions. They obey the Pauli exclusion principle, which forbids them from occupying the same quantum state. As matter is compressed, electrons are forced into higher and higher energy states. This generates a pressure independent of temperature. This pressure does not weaken as the star cools. As a result, the white dwarf stabilizes. It does not collapse into a smaller object unless its mass exceeds a critical threshold. For stars like the Sun, that threshold is never reached. The white dwarf does not shine through internal production. It glows only because it is hot. At birth, a white dwarf's temperature can exceed 100,000 degrees. Over time, it radiates this heat away into space. No new energy is generated. Cooling is inevitable. As the temperature drops, the behavior of matter inside the star changes. The interior of a white dwarf consists primarily of carbon and oxygen nuclei. immersed in a sea of degenerate electrons. At high temperatures, these ions form a dense plasma, moving freely despite extreme compression. As thermal energy dissipates over billions of years, this motion slows. Eventually, the ions can no longer overcome their mutual electric repulsion. They settle into fixed positions. A phase transition occurs. The plasma crystallizes. Carbon and oxygen nuclei lock into an ordered lattice structure, similar in principle to the atomic arrangement in a diamond. This process begins at the core and gradually propagates outward as cooling continues. You see, the star does not become transparent or reflective. It does not sparkle. The term diamond star is a simplification. What actually forms is a macroscopic crystal, planetary in scale, stellar in mass. This phenomenon is not theoretical. One of the most well-studied examples is the white dwarf known as BPM 37093, informally called Lucy. Observations of its pulsation modes reveal that a significant fraction of its interior has already crystallized. Its oscillations behave differently than those of a fluid star. The data indicate a solid core. This confirmation required decades of modeling and precise measurement. The process could not be observed directly. It had to be inferred from how the star vibrates, how sound waves propagate through matter that is no longer liquid. Crystallization in white dwarfs is slow. It unfolds over billions of years. The star cools imperceptibly on human timescales. Civilizations rise and vanish while its internal structure gradually freezes. There is no event marking completion, no sudden transformation. The white dwarf simply becomes more solid, more ordered, and less energetic. This is the future of the Sun. It will not explode. It will not collapse into a black hole. It will shed its outer layers, leave behind a dense core, and cool. Over immense spans of time, that core will crystallize. The Sun will become a silent cooling lattice of carbon and oxygen, no longer a star in the conventional sense, but a stellar fossil. Eventually, even this object will approach thermal equilibrium with its surroundings. Its residual heat will leak away into space. Its glow will fade into the background radiation of the universe. This outcome is not dramatic. It is not rare. It is the default ending for most stars. White dwarfs and their crystallization demonstrate a recurring theme in cosmic evolution. Energy production ceases, structure persists. Matter settles into its lowest accessible energy state. The universe does not rush toward destruction. It cools, it solidifies, it becomes still. Black holes are commonly described as violent objects. They are associated with destruction, collapse, and extreme gravitational forces. This reputation comes not from the black hole itself, but from its surroundings. In physical terms, a black hole is not an active agent. It does not pull, consume, or hunt. It simply exists as a stable solution to Einstein's field equations. In this sense, black holes are among the quietest structures in the universe. The origin of a black hole begins with stellar evolution at the high mass end. When a massive star exhausts its nuclear fuel, thermal pressure can no longer counteract gravity. The core collapses inward. If the remaining mass exceeds the limit supported by neutron degeneracy pressure, collapse continues without a known stopping mechanism. Space-time itself responds by curving inward, forming a region from which no causal signal can escape. This region is defined not by material surface, but by geometry. The defining boundary of a non-rotating black hole is the Schwarzschild radius. This radius marks the distance from the center at which the escape velocity equals the speed of light. Beyond this boundary, all future directed paths through space-time point inward. The event horizon is not a physical membrane. It is a mathematical surface that separates two regions of space-time with fundamentally different causal structures. Nothing special happens locally at the horizon. The laws of physics do not change. What changes is what can influence the rest of the universe. Time dilation near a black hole arises directly from general relativity. As gravity increases, the rate at which time passes slows relative to a distant observer. This effect is not subjective or perceptual. It is built into the geometry of space-time itself. Clocks placed near massive objects tick more slowly than clocks far away. Near a black hole, this effect becomes extreme. To a distant observer watching an object fall toward the event horizon, the infalling object never appears to cross it. Instead, its motion slows progressively. Each signal it emits takes longer to arrive. As the object approaches the horizon, the light it emits becomes increasingly redshifted. Visible light stretches into infrared, then into radio wavelengths, and eventually beyond detectability. The image fades, not because the object is destroyed, but because its time is diverging from the observer's time. From the perspective of the infalling object, this description is incomplete. Locally, nothing unusual occurs at the horizon. The object crosses the Schwarzschild radius in a finite amount of its own proper time. There is no moment of suspension or freezing. The difference between these two descriptions is not a contradiction. It is a consequence of relativity. There is no single universal clock. Time depends on trajectory. This asymmetry creates a form of temporal isolation. From the outside universe, matter falling into a black hole becomes effectively frozen in time. From the inside, the universe outside accelerates. These two realities cannot be reconciled by any observer. The event horizon permanently separates them. Surrounding the event horizon is the photon sphere. This is the region where the curvature of space-time is strong enough that light itself can orbit the black hole. Photons traveling tangentially at this radius follow closed paths, circling the hole before either escaping or falling inward. The photon sphere is not stable. Small disturbances cause light to spiral away or collapse inward. Nevertheless, its existence highlights a critical point. Near a black hole, space is so distorted that even massless particles are forced into curved trajectories. See, the dramatic images commonly associated with black holes originate not from the hole itself, but from accretion disks. When gas and dust fall toward a black hole, they rarely fall straight in. Conservation of angular momentum causes material to form a rotating disk. Friction and magnetic interactions within this disk convert gravitational potential energy into heat. Temperatures rise to millions of degrees. Radiation is emitted across the electromagnetic spectrum. This is where black holes appear violent. The black hole itself, however, remains unchanged by this activity. According to the no-hair theorem, a black hole is completely described by three quantities: mass, charge, and angular momentum. All other information about the matter that formed it is erased from the external universe. Chemical composition, structure, masses, and history are lost. Complexity collapses into simplicity. In this sense, black holes represent the ultimate reduction of information. They are not chaotic objects, they are objects of perfect order. Once formed, they evolve only by slowly accreting mass or, over unimaginably long timescales, by evaporating through Hawking radiation. This evaporation is so slow that for stellar mass black holes, it exceeds the current age of the universe by many orders of magnitude. Spaghettification, often cited as a defining feature of black holes, is a tidal effect rather than a property of the horizon itself. It arises because gravity increases rapidly with decreasing distance. Objects falling toward a black hole experience stronger gravitational pull on their nearer side than on their farther side. This difference stretches the object along the radial direction. Near small black holes, this effect becomes lethal before the horizon is reached. Near supermassive black holes, the tidal gradient at the horizon is gentle. An object could cross without immediate disruption. What defines a black hole is not destruction, but separation. The event horizon marks a boundary beyond which information no longer participates in the shared timeline of the universe. From the outside, matter becomes eternally slowed, redshifted and dim. From the inside, the rest of the universe becomes inaccessible. Black holes do not glow, they do not radiate, they do not announce their presence unless matter interacts with them. Left alone, they are silent. They persist as static distortions in space-time, gradually accumulating mass, gradually simplifying, gradually moving toward equilibrium. In the long future of the universe, when stars have burned out and galaxies have thinned, black holes will remain as some of the last organized structures. Not because they are active, but because they are stable. They are the quietest endpoints of gravitational evolution. They are time slowed to its limit, matter reduced to geometry, motion approaching rest. On the largest observable scales, the universe does not resemble a random scatter of galaxies suspended in empty space. Matter organizes itself into a coherent, filamentary architecture that spans the observable cosmos. This arrangement is known as the cosmic web. Its existence is not aesthetic. It is a physical consequence of gravity, acting on an expanding universe over billions of years. When the universe was young, matter was distributed with remarkable uniformity. Density differences were present, but they were small, variations of only 1 part in 100,000. These tiny irregularities were enough. Gravity amplified them relentlessly. Regions that were slightly denser attracted more matter, becoming denser still. Regions that were slightly emptier lost matter and grew emptier over time. This feedback did not produce spheres or clouds. It produced filaments. Dark matter, which outweighs ordinary matter by a factor of roughly 5 to 1, drove this process. Because it interacts almost exclusively through gravity, dark matter began to collapse early, long before atoms could cool and form stars. Numerical simulations show that as dark matter collapses, it naturally stretches into elongated structures, vast strands that connect nodes of higher density. These strands form the backbone of the cosmic web. Ordinary matter followed the same gravitational gradients. Hydrogen gas flowed into dark matter filaments, where it compressed and cooled. At filament intersections, where gravitational potential wells were deepest, gas accumulated most efficiently. These nodes became the sites of galaxy clusters, containing hundreds or thousands of galaxies bound together. Galaxies, then, are not fundamental units of cosmic structure. They are surface features. What we observe through telescopes is the luminous residue tracing a much larger, invisible framework. Remove the dark matter and the web collapses. Remove the galaxies and the structure remains. Filaments are not static beams frozen in space. They are dynamic channels, gas streams along them continuously, feeding galaxies and clusters. This inflow sustains star formation over billions of years, regulating how quickly galaxies evolve. When the inflow slows or stops, galaxies age, redden, and fade. Between these filaments lie the voids. Cosmic voids are not small gaps. They dominate the universe by volume. A single void can span hundreds of millions of light years and contain almost no galaxies at all. The Boötes void is one of the most prominent examples. A region so underdense that early surveys struggled to explain its existence. In voids, gravity has already done its work. Matter has drained away toward denser regions, leaving behind expanses where particle densities approach the cosmic minimum. A few faint galaxies may remain, but interactions are rare. Star formation is weak, evolution slows. From a thermodynamic standpoint, voids are not exceptions. They are the expected outcome of matter seeking lower energy configurations. As mass concentrates into filaments and nodes, emptiness expands elsewhere. Structure and emptiness grow together. On scales larger still, filaments and clusters participate in coherent motion through space. Our galaxy belongs to the local group, which is part of a vast supercluster called Laniakea. This structure spans more than 500 million light-years and contains tens of thousands of galaxies. Laniakea itself is not gravitationally bound as a single object. It is defined by a common flow pattern. Galaxies within this region are moving toward a gravitational basin known as the Great Attractor. The Great Attractor is not a single mass, nor is it directly observable. It lies partially hidden behind the dense plane of the Milky Way. Its presence is inferred from velocity measurements. Galaxies in our cosmic neighborhood exhibit systematic deviations from uniform expansion. They are drifting in a preferred direction. The Milky Way, Andromeda, and the rest of the local group are moving at approximately 600 kilometers per second relative to the cosmic microwave background. This motion is not propulsion. There is no force pushing us forward. There is no destination. We are slided down a gravitational gradient defined by the large-scale distribution of matter. The motion is passive, inevitable, and shared by everything in our region of space. When visualized, the cosmic web often resembles branching networks, strands converging at hubs separated by large cavities. This resemblance is geometric only. It does not imply signaling, coordination, or purpose. Similar shapes emerge whenever matter flows along gradients under constraint. Rivers, cracks, and fractures obey the same mathematics. The cosmic web is therefore not alive, and it is not communicative. It is mechanical. Its structure reflects how gravity organizes matter when given sufficient time and insufficient opposition. Crucially, this structure is temporary. As the universe expands, dark energy accelerates that expansion. Over time, filaments stretch, clusters relax internally, converting motion into heat and radiation. Void regions grow larger and emptier. Eventually, the distances between structures increase faster than light can cross them. When that happens, the web dissolves, not physically, but causally. Galaxies beyond a certain distance can no longer influence one another. Their gravitational connections weaken until they are effectively isolated islands in an ever-expanding sea of space. The cosmic web is a snapshot of the universe during its structured Middle Age. It exists only because expansion has not yet erased gravitational connectivity. It persists only because energy gradients remain. In deep cosmic time, those gradients flatten, filaments thin, nodes dim, voids dominate. What appears to us as a richly connected universe is, in reality, a transient arrangement, one that occupies a narrow window between early uniformity and late isolation. The web does not tighten, it loosens, and eventually, even its largest structures become indistinguishable from stillness. The material composition of the universe has not been constant. At its origin, the universe was chemically simple. In the first few minutes after the Big Bang, conditions were hot and dense enough for nuclear reactions to occur, but only briefly. As expansion proceeded, temperatures dropped too quickly to sustain complex fusion. The result was a universe composed almost entirely of hydrogen, helium, and trace amounts of lithium. No carbon existed, no oxygen, no nitrogen, phosphorus, iron, or calcium. The elements required for chemistry, geology, and biology were absent. For hundreds of millions of years, this simplicity persisted. Matter cooled. Density fluctuations grew. Gravity gathered gas into the first stars. These stars were not merely luminous objects. They were the universe's first chemical engines. Stellar nucleosynthesis is the process by which stars manufacture new atomic nuclei through fusion. It is the mechanism by which a chemically barren universe becomes complex. Inside a star, gravity compresses matter to extraordinary pressures and temperatures. In these conditions, atomic nuclei collide with sufficient energy to overcome their electrostatic repulsion. When they fuse, mass is converted into energy and new elements are formed. The earliest stars fused hydrogen into helium. This process released energy and sustained stellar luminosity, but it did not significantly alter the chemical inventory of the universe. Helium was already abundant. The critical transformation occurs later. As stars exhaust their hydrogen fuel, their internal structure changes. Cores contract, temperatures rise. In sufficiently massive stars, new fusion pathways become possible. Carbon is created through a mechanism known as the triple alpha process. Helium nuclei, alpha particles are stable, but carbon is not formed easily. Two helium nuclei can briefly combine to form beryllium-8, an unstable isotope that decays in fractions of a second. Under normal conditions, it vanishes before anything further can occur. Inside stellar cores, density and temperature are high enough that a third helium nucleus can collide with beryllium-8 before it decays. When this happens, carbon-12 is formed. This process is finely balanced. If nuclear resonance energies were slightly different, carbon production would be inefficient. Stars would fail to synthesize the element that underpins organic chemistry. The universe would remain chemically impoverished. Once carbon exists, the additional fusion pathways open, carbon can fuse with helium to form oxygen. In more massive stars, fusion continues beyond this point. Neon, magnesium, silicon, sulfur, and eventually iron are produced in successive burning stages. Each stage requires higher temperatures and yields less energy. Iron marks a limit. Fusing iron does not release energy, it consumes it. When a stellar core becomes dominated by iron, fusion can no longer support the star against gravitational collapse. At this point, the star's fate is sealed. In high-mass stars, collapse occurs catastrophically. The core implodes, outer layers rebound violently. A supernova is triggered, Supernovae are not simply explosions, they are redistribution mechanisms. During the collapse, conditions become extreme enough to synthesize elements heavier than iron through rapid neutron capture. Gold, uranium, iodine, and many other heavy nuclei are formed in fractions of a second. When the star explodes, these newly created elements are expelled into space at high velocity. The surrounding interstellar medium becomes chemically enriched. Gas clouds that were once composed primarily of hydrogen and helium now contain carbon dust, oxygen atoms, iron grains, and complex molecules. Over time, this enriched material mixes, cools, and collapses again. New stars form. But unlike the first generation, these stars are born into a chemically diverse environment. Their planetary systems inherit heavy elements. Rocky planets become possible. Atmospheres can retain complex molecules. Chemistry gains depth. The solar system formed from such enriched material. By the time the Sun ignited, the galaxy had already experienced billions of years of stellar evolution and death. Countless stars had lived and collapsed, each contributing a small fraction of their internal matter back into the galactic reservoir. The atoms that now compose Earth were forged in multiple stellar interiors. The carbon backbone of DNA was synthesized through helium fusion in long-dead stars. The oxygen you breathe was produced in stellar cores and expelled by supernovae. The iron in hemoglobin was assembled in massive stars shortly before their collapse. The calcium in bone was generated in environments far hotter than any planet has ever experienced. These atoms did not arrive together. They drifted independently through the interstellar medium for immense spans of time. They participated in multiple cycles of collapse and dispersal. Eventually, a small fraction of them became incorporated into the protoplanetary disk that formed Earth. Biological life did not introduce new matter into the universe. It rearranged existing matter. From a physical perspective, a living organism is a temporary configuration of atoms assembled under favorable conditions. Metabolism, growth, and reproduction are processes that move atoms through complex molecular pathways, but they do not change their origin. The distinction between organic and inorganic matter is functional, not fundamental. There is no chemical boundary separating a human body from an asteroid. Both are composed of nuclei produced by stellar fusion. Both obey the same physical laws. The difference lies solely in molecular arrangement and energy flow. This continuity eliminates any sharp division between the observer and the observed. The matter that forms eyes capable of seeing the universe is the same matter that was shaped by that universe long before those eyes existed. Observation is not external to cosmic processes. It is one of their late-stage configurations. The atoms that compose a person are billions of years old. They have existed in states of plasma, gas, dust, rock, and now biology. This current assembly is transient. Given enough time, these atoms will disperse again, return to the environment, incorporated into new structures, or carried outward as space expands. Nothing about their origin privileges their present form. Life is not a separate category of matter. It is a brief chemical arrangement made possible by the universe's earlier era of stellar activity. When that era ends, no new heavy elements will be produced. Existing atoms will persist, but their rearrangement into complex systems will become increasingly rare. Chemical richness is therefore historical. It depends on stars that no longer exist and processes that will not repeat indefinitely. In this sense, Every biological structure is a fossil of stellar evolution. Not metaphorically, literally. We are not made of star stuff in a poetic sense. We are made of the physical byproducts of fusion reactions that occurred in stars that lived, collapsed, and vanished long before the present moment. The universe does not remember those stars, but their matter remains. The long-term evolution of the universe is not governed by catastrophe. It is governed by thermodynamics. At every scale where physical processes occur, the energy tends to spread. Differences in temperature, pressure, and density diminish over time. This tendency is formalized in the second law of thermodynamics. In an isolated system, entropy does not decrease. Entropy is often described as disorder, but this is imprecise. More accurately, entropy measures how evenly energy is distributed. Low entropy corresponds to strong gradients, hot next to cold, dense next to empty. High entropy corresponds to uniformity. The universe began in a state of extraordinarily low entropy. Energy was concentrated, matter was unevenly distributed. Over time, gravity amplified these differences, creating stars, galaxies, and structure. This increase in complexity did not violate the second law. It was driven by it. Structure forms because energy is still redistributing. But redistribution has a direction. As usable energy is consumed, the capacity to do work declines. Eventually, the conditions that allow stars to exist disappear. Cosmological models predict that star formation will cease when galaxies exhaust their reservoirs of cold gas. Hydrogen will either be fused into heavier elements or locked away in stellar remnants. Without sufficient raw material, no new stars can ignite. This transition marks the beginning of what is known as the degenerate era. During this era, the universe does not suddenly go dark. Existing stars continue to burn. Low-mass red dwarfs, which consume their fuel extremely slowly, persist for trillions of years, but no new luminous objects replace those that fade. Gradually, the population of active stars declines. What remains are stellar remnants, white dwarfs, neutron stars, and black holes. These objects no longer generate energy through fusion. They cool, collide, merge, or remain inert. Galaxies lose their defining feature. Light becomes scarce. As time advances further, even these remnants evolve. White dwarfs cool toward black dwarfs, objects that emit almost no radiation. Neutron stars lose rotational energy. Occasional mergers occur, producing brief flashes of radiation, but such events become increasingly rare as expansion separates matter. Eventually, the universe enters the black hole era. At this stage, black holes dominate the mass budget of the cosmos. They exist at the centers of former galaxies and as the products of countless stellar deaths and mergers. In a universe where other energy sources have faded, black holes represent the final reservoirs of concentrated mass energy. Despite their reputation, the black holes are not eternal. According to quantum field theory in curved spacetime, black holes emit radiation. This process, known as Hawking radiation, arises from quantum fluctuations near the event horizon. Particle-antiparticle pairs briefly appear. In certain configurations, one particle escapes while the other falls inward. From the outside, the black hole appears to lose mass. This radiation is extremely weak. For stellar mass black holes, the temperature associated with Hawking radiation is far below that of the cosmic microwave background. They absorb more energy from their surroundings than they emit. Only when the universe cools sufficiently does net evaporation begin? The timescales involved are immense. A black hole with the mass of the Sun would require on the order of 10 to the power of 67 years to evaporate completely. Supermassive black holes require vastly longer, up to 10 to the power of 100 years or more. During this era, the universe is extraordinarily simple. There are no stars, no planets, no chemistry driven by energy gradients, only isolated black holes slowly losing mass, surrounded by an ever-expanding, ever-cooling sea of radiation. Eventually, the last black holes evaporate. When this happens, the universe transitions into its final stage, the dark era. In the dark era, matter as we know it may no longer exist. Protons may decay, if such decay is allowed by fundamental physics. Atomic structures cannot persist indefinitely without energy input. What remains is a dilute bath of low-energy photons. Neutrinos and possibly electrons and positrons spread thinly across an enormous volume of space. Temperature differences approach zero. Energy gradients vanish. The universe reaches a state of maximum entropy. In this condition, no macroscopic processes are possible. There is no heat flow because there is no hotter or colder region. There is no work to be done because energy is evenly distributed. Time may still pass in a formal sense, but nothing changes in any meaningful way. This is the heat death of the universe. It is not an explosion. It is not collapse. It is not destruction. It is a gradual asymptotic approach to equilibrium. The universe does not end. It becomes static. This outcome is not pessimistic. It is neutral. It reflects the most statistically probable configuration of energy in an isolated system given sufficient time. From the perspective of deep time, the active universe we inhabit now is the anomaly. Stars burning, galaxies interacting, chemistry flourishing. These are transient phenomena made possible by temporary energy gradients. As those gradients flatten, activity fades. The final universe is quiet, not because something went wrong, but because nothing is left to happen. Entropy has completed its work. What remains is a cosmos in perfect thermodynamic balance, unchanging, diffuse, and silent. This is not a violent ending. It is rest. The accumulation of physical evidence presented throughout this analysis leads to a single unavoidable recalibration of perspective. This recalibration is sometimes referred to as the overview effect, a cognitive shift reported by astronauts when viewing Earth from orbit. In its popular form, the concept is framed emotionally. Here, it is treated as a data-driven correction. Human perception evolved under constraints that favored immediacy, proximity, and survival relevance. Scale was never a selectable trait. The nervous system is optimized for meters, seconds, and lifetimes measured in decades. As a result, when confronted with astronomical quantities, billions of years, trillions of stars, expansion on cosmological horizons, the mind attempts to compress them into familiar narratives. This compression introduces distortion. The physical description is unambiguous. Earth is a terrestrial planet with a radius of approximately 6,000 kilometers, orbiting an average G-type main sequence star at a distance of 1 astronomical unit. That star is one of roughly 400 billion stars gravitationally bound into the Milky Way galaxy. The Milky Way itself is a mid-sized spiral galaxy located on the outskirts of a supercluster structure known as Laniakea. Laniakea is one of countless such structures embedded in the observable universe, which contains on the order of 2 trillion galaxies. This is not a poetic framing, it is a census. From this vantage, the concept of human centrality becomes statistically untenable. Biological life on Earth occupies a thin atmospheric layer on the surface of a single planet. Its entire recorded history spans a fraction of a second when placed on a logarithmic cosmic timeline. This is not a statement of worth or value. Physics does not assign value, it describes distribution. The psychological discomfort often associated with this realization stems from a category error. Insignificance is interpreted as negation. In reality, it is a resolution issue. When an object is examined at the wrong scale, it appears either exaggerated or diminished. Adjusting the scale restores accuracy. From a cosmological perspective, human concerns do not vanish, they localize. Conflict, ambition, fear, and aspiration remain real within their appropriate frame of reference. What dissolves is the assumption that these phenomena exert influence beyond their physical domain. The universe does not respond to intention. It responds to mass, energy, and curvature. This reframing does not induce nihilism. Nihilism implies the absence of structure or meaning. The data indicates the opposite, an excess of structure operating independently of observation. Galaxies form whether or not they are named. Stars ignite regardless of whether they are witnessed. Entropy increases without audience. Accuracy replaces self-importance. The correction is stabilizing. When viewed at sufficient scale, urgency diminishes. Not because events cease to matter locally, but because they are revealed as transient perturbations in a system whose baseline state is continuity. The overview. Effect stripped of sentiment is the acceptance that the universe is not oriented toward us. It simply includes us briefly as a configuration of matter moving along a thermodynamic gradient. Across every scale examined, from quantum fields to cosmic voids, from stellar life cycles to the ultimate thermodynamic fate of the universe, a consistent pattern emerges. Activity is the exception. Stillness is the rule. Stars burn for billions of years, yet this phase represents a temporary release of stored gravitational energy. Their formation is followed inevitably by cooling, crystallization, and decay. Galaxies collide, but the collisions occur across timescales so vast that individual stars rarely interact. Black holes grow not through violence, but through slow accretion and the quiet curvature of space-time. Even their disappearance occurs through Hawking radiation, a process so gradual that it resembles waiting rather than destruction. Between these events lies the dominant architecture of the cosmos, expanding space, or thinning matter, cooling radiation. The universe is not filled with objects, it is structured around absence. The vast majority of its volume contains no stars, no planets, no life, only dilute fields and background photons stretched to ever longer wavelengths. The luminous structures that attract attention exist as filaments and nodes embedded within an overwhelming expanse of void. From this perspective, silence is not emptiness, it is equilibrium in progress. The future described by physical law is not abrupt, it is asymptotic. Processes do not end, they approach limits. Temperature approaches zero, energy gradients flatten, events become less frequent until they effectively cease. The dark era is not a moment in time, it is a condition. This understanding reframes the present. Anxiety, urgency, and noise characterize biological perception because life exists far from equilibrium. Metabolism requires imbalance. Thought requires electrical gradients. Emotion requires chemical asymmetry. These are local conditions, not universal ones. Beyond the narrow window in which life operates, the universe trends toward rest. This does not negate experience, it contextualizes it. The universe does not require interpretation to function. It does not accelerate for observers or pause for reflection. It continues according to its governing equations, indifferent to narrative. Observation does not grant permanence, it merely records a temporary state. In the opening moments, a single point of light was introduced against darkness. That point represented matter, energy, and attention concentrated into a detectable signal. In conclusion, that signal fades, not as a loss, but as a return. What remains is the underlying structure: expansion without destination, time without events, space without markers. The prevailing condition of reality is not chaos. It is a long, uninterrupted drift toward equilibrium. The universe does not ask to be understood. It does not require observation to exist. It simply continues.